response to an email message you sent me.
Did I not respond? I'm sorry. Yes, I got your email message and I got it, and in my mind, I thought I responded, but I got you set up. We'll be good. All right, so we worked one. That's what we did last time. And so we worked it with Gaussian elimination. And so we are to this problem. I'm going to blow it up for just a second, and then I'll make it small again. So we're going to work this one, and I want to work it by Gauss-Jordan. So that means that I want to work it all the way out in row echelon form. So I want to get only ones and zeros in the coefficient matrix. And then when I get it in ones and zeros in the coefficient matrix, that means that it'll be boom. I know X and Y and Z. So that is the plan. Now I'm going to open my notes so that I can check myself. Because if I make one little error, we've wasted our lives. Just a few minutes of our lives. That's it. Okay. All right, now remember that there's more than one way to work it. So some of you might say, okay, I'm going to say 1/2 row 1 gives me a new row 1 because that'll give me a 1 in that top position. So you could certainly start it that way. But I'm going to, where I don't have fractions off the bat, I'm going to just interchange rows 1 and 2. So that's how I'm going to start it. Because here's where I'm going, just where you know where I'm going. Okay, that's what I'm trying to get to. And so my order of operations that I'm going to do is I'm going to get a 1 here first, and then I'm going to get these zeros. And then I'm going to get a 1 here first and use that 1 to get these 2 zeros. And I'm going to get a 1 here and use that to get those zeros. So that is my plan. Now I write out every step, as you know. So I'm going to write out my operations, but you don't have to, unless you want to. So I'm going to say row 1 and row 2, and I'm going to switch them. What I should have done first, though, that I realized I didn't do, was I should have written it as a matrix first. So I'm going to go ahead and do that over here. And the other thing that I always told you I do first is double check it to make sure I copied it right, which I didn't do that either. Goodness. Okay, and now I like it. So we're rolling now. Are there any questions with it so far? Okay, so I'm going to interchange rows 1 and 2. Great. Now then, I'm going to get rid of this 2 right here. So to get rid of that 2, I'm going to use this 1 right here to take care of that. So I'm going to say -2 times row 1. I'm going to add that to row 2, and that's going to change my row 2. Now the way that we're going to think about that is that row 1 is going to stay the same. You'll say, oh, but you're multiplying it. I'm multiplying it by 2 so that I can use it for something, but I'm not actually changing row 1. I'm changing row 2, so that one's going to change, and row 3 is going to stay the same. Hey, now some of you can do that red step in your head. That's perfectly fine. As you know from me already, I don't do anything in my head. So feel free to do it in your head if you'd like. Just be really careful with your signs. Must admit, I was really nice to you on this one. It comes out to be very, very nice. Now, my whole purpose with that part, or the whole procedure, I suppose, is to get the 1 and the zeros beneath it. Sweet, we have worked our first column. Okay, so take a minute. I'm going to give you a minute, rather, to catch up, look at it, see if you have any questions, anything like that. Okay, so the next thing I'm going to do, you could have even done it here if you wanted to. You could do 2 steps at once. So I'm going to get a 1 in the next column. And of course, I want that 1 in that center position. So to get this 1 right here, I'm going to say negative 1/7, row 2, gives me a new row 2. Row 1's going to stay the same. Row 3 is going to stay the same. And I'm going to get 0, 1, 0, 5. So I know y is 5. I'm going to use that 1 in the middle in order to get the 2's to be gone. Okay, so I've run out of room, so I'm going to take this matrix here, recopy it on the next slide. Yes, they do that. So when the boards start getting older, they take away keystrokes. And so you'll see me sometimes go, because that makes it pop up. Anyway, it's time for new boards or new screens or Apple TVs or whatever the next thing is. We've reached our limit of, because they're like maybe 10, 12 years old. They're old. All right, so let's double check to make sure I copied it right, because otherwise you know where it will go. 1, 2, 1, 2, 1, 0, negative 1, 17, 5, 7. Okay, I like it. All right, so now then, we're going to get rid of the 2's. So I'm going to say, I'm actually going to do them at the same time. Good morning. That's okay. So we're going to say negative 2, row 1. Negative 2, row 2, plus row 1. And that's going to change my row 1. And I'm also going to say negative 2, row 2, plus row 3. And that's going to change my row 3. I'm just going to try to save us a little bit of time. All right, so this is going to be 0, negative 2, 0, negative 10. I'm going to add it to the top row. Okay, so negative 2 times row 2. Add that to row 1. And that's what I get. So instead of rewriting it all and doing it again, I'm just going to go ahead and work from here. So I'm going to say negative 2, row 2. And that's what my new row 3 would look like. But I'm not going to write it in. I am going to write it in just like it is. You probably see where I'm going with this. You could have also gone ahead right then, and you could have said negative 1, row 3 gives me a new row 3, and so you would have 0, 0, 1, 3. That would work. But I'm looking ahead to where I'm going, and the place I'm going is to get rid of that 1 in the third column of row 1, right? And so if I leave it as a -1, all I have to do now is add row 1 and row 3. Are there any questions with it? Okay, so taking what I have up here, I'm going to say row 1 plus row 3. Now, row 1 is the one I want to change, because remember, I'm trying to get rid of this guy right here. So I'm going to change row 1. So I get 1, 0, 0, 4. All right, so my row 1 looks great, and my row 2 looks great. Row 3 does not. So I'm going to go back to the row 3. Remember, I need a 1 there. Well, that's easy to fix. I'm going to say -1 row 3 would replace my row 3. Now that looks great. And truly, I like all of you, so I would give you full credit for that particular answer, but that's not really an answer. Because remember, the goal here, or what we're trying to do, is solve the system. So when you solve a system, you can either write it as an ordered triple in this case, or write it as x and y and z, but you don't just leave it as a matrix. So the purpose of Gauss-Jordan elimination is that it puts it in the form, so this would say 1x plus 0y plus 0z equals 4. 0x plus 1y plus 0z equals 5. 0x plus 0y plus 1z equals 3. So your column of constants there is actually your solution set. You could also write it this way. Okay, and that's called Gauss-Jordan. I won't make you work, I think I might make you work Gauss-Jordan on a homework problem, but as far as on a test, Gaussian elimination or Gauss-Jordan, either one should work. We're almost done, yay. Are there any questions with that one? And Natalie, I know you missed the first part, but remember it's all videoed, and so you'll be able to either pick up the notes in the section, or you'll be able to pick up the video in the section and get what you missed, okay? So don't worry about trying to frantically copy it. All right, here is your next one on the sheet. All right, so it's just going to say solve. It doesn't, but it should. Sorry about that. You'll say, what does it say up there that's highlighted? That's a note to myself to talk to you about consistent and inconsistent, because that's something that I'll ask you on your test. All right, so I'm going to use this problem to explain it. So I've got 1, -3, 1, and 1, and 2, -1, -2, 2. And 1, 2, -3, -1 is how that one looks. Let me double check it. Okay, because I think that you know how to do this already, I'm going to go a little quickly through this first part. And so if I go a little fast, just know that just get to this next point, and then you can, go back and look back over your notes and figure it out. I'm going to get a 1 in the top position, which I have, and then I'm going to get rid of this 2, and then I'm going to get rid of this 1. So I'm going to do both that red operation and that blue operation just kind of in one little wallop. So to get rid of the 2, I'm going to say -2 row 1 plus row 2. And that's going to give me a new row 2. So that means that row 1 stays the same. I'm going to move out of your way in a second. I'm blocking you. Okay. Okay, so when I get my new row 2, that's how it should look. Okay, so to get rid of the blue value, I'm going to say -1, row 1, plus row 3 would give me a new row 3. And then it looks a little funny. So it looks a little funny. No, I meant for it to look a little funny. That's what's going to happen. I'm going to stay consistent. Some of you know, I would just say, I would say I'm going to stay consistent, and so I'd turn that red 5 into a 1, but I just have to turn it back to a 5, right? So remember where I'm going with this is I want that bottom row to get a 1 where that 4 is. So what I could say at this particular point is let's not get it to a 1, even though that's our usual case. Let's take this red and blue matrix here and get rid of this guy. So in order to get rid of this guy, I'm going to say -1 times row 2. I'm going to add that to row 3, and that's going to give me a new row 3. But I have a little spidey sense, so because something doesn't look quite right, they look like a lot alike, right? And so when you get your matrices and they start looking alike and the rows start looking alike, you know, ooh, I think this is going to be a special case. So that's your thought process. Now, again, I'm skipping some steps to go to this green step. You could turn the red 5 into a 1, say 1/5 row 2 gives me a new row 2. And then after you do that, then you turn it into a -5 to make this 5 go away. Okay, so I just kind of skipped over that part. So I'm going to say 0, -5, 4, and 0. And when I add them up, this is what I get. So I get, I'm out of room, sorry, but I get 0, 0, 0, -2. So this bottom row is going to look like this. Now, I can rewrite the tops if I needed to. Just leave it alone. Okay, so that's how the matrix is going to simplify. So if I read across the bottom, it says 0x plus 0y plus 0z, which would all be 0, right? Equals -2. Well, when does 0 equal -2? Never. And so it's a no solution. Okay, will I give you one like that? Yes, I actually like giving you those because they're easier than the parameter ones, right? There's no parameter, it's no solution. That means nothing works, right? So that's how one of those would play out. Now, at the top of the page, I talked to you about consistent and inconsistent. And there's a definition somewhere in your notes about inconsistent and consistent. This one right here is inconsistent because that means there is no solution. Now, if it has any solution at all, it's called consistent. Whether it has a traditional solution like the one on our previous slide, or whether it has a parametric solution, if it has any solution at all, it's called consistent. But if it doesn't have a solution, it's called inconsistent. Are there any questions with this problem or that definition? Okay, so I'm going to write the consistent part, and this is in my words, not textbook words. Okay, so if it's consistent, it is consistent rather if it has any solution at all, whether it's one or infinitely many.
You said that's that particular.
This particular one is inconsistent. So as soon as we got a no solution right here, we know that this one is inconsistent.
You got that because you can't have a variable, a 0 equal -2.
0 does not equal -2. That is true. That's how I knew that. Let me answer that. Let me explain that a little differently. At the end, I got a false statement. So if I get a false statement at the end, I know it's a no solution. Very good question. All right. Next. I'm not ready to do that one. That's not the one I wanted. All right, so I am going to do that one, but I wanted to put one more in there. Okay, so find a little side piece of paper for me, and I'm going to do this one. Now, I know this wasn't in your sheet, so I'm going to give you time to get caught up.
You just write this one down.
Yep.
Are we going to do the next page?
We are going to do that next page, so don't write it there. The good thing about it not being in your notes is that if I write a problem on this screen myself without pulling it in, I get to make it bigger and smaller and I get to use the whole board. But if I bring in something, just where you know why sometimes I can make it bigger or not, if I bring in, like if I brought this in, if I can make it bigger, but then once I write on it, I can't, it doesn't help me. So that's why sometimes I can move the board and sometimes I can't, if you were wondering. Okay. Well, there it is. Okay. So we're going to solve this down. Let me double check all my signs. Please double check all your signs. Now then. Lots of ways to go with it. I think I was leaning toward saying 1/2 row 1 gives me a new row 1 because it just gives me one slight little bitty fraction, but then it's going to take care of the ones below it. But I think my easiest route, but of course there's lots of different ways. We're all going to get the same answer regardless of which way we pick. But I think that what I really want to do is I'm going to move row 1 and row 3 because that one seems like the smallest of it. And I'm even going to do 2 steps at once. I knew when I move row 1 to when I interchange rows 1 and row 3, I need a 1 in the top. So the other thing that I'm going to do once I move this to the top is then after I move it, I'm going to say -1 row 1 gives me a new row 1. So I'm going to do more than one step at a time. Okay, so I'm going to move this guy right here to the top, interchange them, and once I move it to the top, I'm going to multiply it through by -1. Now then. That's much more usable. I kind of did 2 steps at once, and that's okay. Row 2 stays the same. And row 3 is now the top line, remember? So I interchanged rows 1 and 2, and then once I did that, I said, okay, this is my new row 1, multiply it through by -1. Great. Any questions with that part? Go ahead.
I think the second column needs to be changed to positive.
It does. Joseph, thank you. So see this one right here? That's a mistake. Thank you. All right, now then. So now we're going to use our Gauss-Jordan. I've got the 1 in the top position. I'm going to get rid of the -1, and I'm going to get rid of the 2. So here we go. For the first one, to get rid of this guy, I'm going to say row 1 plus row 2. And that's going to give me a new row 2. That means row 1 is going to stay the same. Okay, and after I do the blue step, let's do green. So I'm going to say -2 row 1 plus row 3 gives me a new row 3. Okay, row 1 plus row 2 gives me a new row 2. Okay, so then I'm going to say -2 times row 1. We'll add that to row 3. I get and then I see something funny is about to happen. Okay? So we're just working it down. And so when you first look at this, you have no idea if it's going to be a special case or not. You just have to work it down to see, right? So as soon as I start seeing these numbers repeat in the rows, I know something is amiss. Do you have any questions with the red or the blue so far? Okay, some of you are still writing, so I'm going to give you a chance to get caught up because I did a lot of stuff at one time. Are there any pieces I need to go back through? Okay, so at this point, I recognize that it's going to be a special case. I don't really know. I know because I've done it so long, but we might not really know if it's going to be a no solution or an infinitely many solution, but we know something's not quite right about it. All right, so I'm going to leave the top row alone. There's nothing wrong with that one. But if I look at the blue and the green rows, I am going to leave the top row alone. I'm going to rewrite it. But if I look at the blue and the green rows, I can say row 1, that's 2, sorry. Row 2 plus row 3 would give me a new row 3. I'm going to leave the blue one alone. So row 2 looks like this, and row 3 looks like this. And when I add them up, I get this. Okay, so Will asked a question earlier about, so you said that 0 equals something, and it took me a while to get the proper answer to his question. So if I look at this time, this bottom row, I get 0x plus 0y plus 0z, which would all be 0 added together, equals 0. And so if I get 0 equals 0, I know that that is a true statement. So as soon as I get an answer that looks like that, my answer is going to be infinitely many. which on your test would get you partial credit, but on your test it doesn't give you full credit. And some of you had your homework assignment that you turned in. You told me one of your problems was infinitely many, which was correct, but you didn't write it with the parameter. So infinitely many is okay, but you have to continue it. Okay, and so by infinitely many, that doesn't mean that every number in the whole wide world works. So you couldn't say 111 works, 888 works, -1, -3, -15 work. So it's not every number in the whole wide world, but it's every number that fits, or every ordered triple that fits this pattern. So you have to describe the pattern, and that is the hardest part. Okay, are there any questions getting to that point? Okay, so here's how I describe the pattern. Here we go. I'm going to rewrite the top row. So the top row is x plus 3z equals 6. And I'm going to rewrite the second row. Y plus 4z equals 6. Okay, and then I'm going to double check to make sure my numbers are right. Okay, I like it. What do both the red and the blue equations, what do they both have in common? They both have the variable z. Okay, so what we're going to do with these is we're going to let z be our free variable. So we're going to let z be t. Okay? Because they both have it. So that's that's my good rule of thumb there. So if I solve this red one, I'm going to get x equals 6 minus 3z. So that's actually going to be that x equals 6 minus 3t. When I solve this blue one, I'm going to get that y equals 6 minus 4z. So that means that y equals 6 minus 4t. So when I get ready to write this one infinitely many of the form, remember x comes first, so it's going to be 6 minus 3t, and y comes next, 6 minus 4t, and z comes next, t. Now some of you might have said, well, I chose to let x be my t. That's fine. You're going to have a different parameterization than I do, but it's still going to be correct. So let's pretend for a second that t was 0, because that's what a parameter means. It can take on any value. If t was 0, then the ordered triple 6, 6, 0 would solve this system. Let's say that t was 1. If t was 1, then 3, 2, 1 would also solve this system. So there are infinitely many things, because we could pick t to be infinitely many numbers, right? We could pick t to be 1,000. I'm not going to do that one in my head. But you could say 6 minus 3,000, 6 minus 4,000, 1,000 would also be a solution to this system. And that is how you'd work it. Look at you doing it in your head. So that's how that particular one would flow. Any questions? You'll say, okay, now what's my answer? You're rambling. This is my answer right here, this whole thing. Okay, the next one that you have is called homogeneous. And what homogeneous means is that it's a system of equations in which each constant term is 0. Now, we're not going to solve that out today because we don't have time. We are going to finish the notes sheet, though. I'm going to give you a couple of other notes. Now, what's special about homogeneous is it always has a solution. So we could say they are always consistent. Okay, so here's why, always consistent. Because if it's a solid row of zeros, then it's called the trivial solution. So the trivial solution, and it's always called the trivial solution, is 0, 0, 0. That's always going to solve it. Now, sometimes other stuff solves it as well, so there'll be additional solutions, but 0, 0, 0 is always going to solve a homogeneous set because 0 minus 0 plus 3 times 0 is 0. And 2 times 0 plus 0 plus 3 is 0 would also be 0, so 0, 0, 0 always solves it. Now, so with that, either it's just going to have one solution that's trivial, or it's going to have infinitely many solutions. And that ends up being a huge foundation piece later for us in the semester. Now, I'm going to come back to this slide next Wednesday and talk about it, because it is really important. All right, one more thing I want to show you. Okay, I'm not going to work this problem. You're welcome to work it if you want, but it ends up being a 5 by 5 equation, I think, system. The purpose of this is to show you where matrices might be used in later life, especially those of you who are engineers. When I think of this particular box here, a lot of people use it with electrical circuits, so you have boxes like this. But when I think about it, I think most of you are the DeSoto area, but when I think about it, I think about going to Oxford and trying to get on West Jackson on Highway 6. You can think of it like a traffic pattern. So you have these intersections. I'm going to blow mine up for a little bit. You have yours on your paper. But you have these junction boxes, or you could also think of them as intersections. You can think of it as the flow of water coming into a certain drainage ditch, you know, that type of thing. So like this one right here, it has something, if you look, it has little arrows. So it's got 20 coming in. I can't tell which way it goes. Okay. Okay, X1 is going out, okay? And X2 is also going out. So what's coming in has to equal what's going out, and so that's how they get a linear equation from that junction box. Okay, so if you look at box 2, X4 is coming in, and X3 is coming out. Okay, so for this one, 20 and X3 are coming out, and X4 is going in. And so you see what's happening. So if we look at junction box 3, X2 is coming in and X3 is coming in. And 10 and 10 are leaving, so that would be 20 that are leaving. And so that's how your junction boxes are going to look. And so my eyes are failing me because those are so tiny small. So I'm going to write them properly, but by the time we come back to class next Wednesday. But that's how that part's going to look. And you see there that you have the junction boxes. They make a matrix. You solve the matrix out. This particular one is infinitely many solutions, but they're of a certain water flow or traffic flow, or, you know, so you're going to be looking at what an optimal solution for that would be. All right, in your possession, you have an assignment. It's hybrid assignment number 2. I'm going to peep at it for just a second. Oh, and I've got your old assignments. I forgot about that.
I guess I would have thought of asking about
Yes.
when to get this assignments, because I saw that like the homework was graded.
Yes, I just graded it today. All right, so you have this weekly assignment number 2. Let's postpone that because you didn't get a chance to ask me any questions with it. Remember, Monday's a holiday, so you have Wednesdays when I initially said it would be due. Wednesday's going to be our review day. You're welcome to turn it in Wednesday, and I can grade it and give it back to you at the end of class if you want to do that. But your test is going to be the following Monday. Okay, so I think Labor Day is the 1st, so your test is going to be 9/8. Okay, that's also when your weekly assignment number 2 is going to be. Now, I'm going to give you these back, and you don't have time to ask me questions on it today, but when you bring it to class on Wednesday, I'm going to finish up the 2 slides that I've yet to do, and then I'm going to answer questions about this, and I'm going to answer questions about your weekly assignment, and then we'll review the rest of the day. So that is our plan.
So some of the things that cover today, with like answer number 2, homogeneous system of linear equation has what characteristic?
Okay, so it has this characteristic that all the constant terms are 0, and it also has this characteristic that it's always consistent.
Oh, so the constant matrix would be a null matrix in that kind of case? If that's a phrase that's used, kind of like how null vector is used?
It would be I would say yes. It would be a null column matrix, which would make it a null vector, yes. Which is going to be huge later because it's going to tell us about if it is linearly independent or linearly dependent, or if it spans.
It's like, could that be like what I say? It's like the column matrix is either a null column matrix, or I could say like a null column vector or a null vector, maybe.
Uh-huh.
One of those.
All of those, yep. That's great. All right, so if you have any questions for me, just stick around. Otherwise, nothing is due Wednesday. Please enjoy your holiday, and then we're just going to back up and get our minds straight before your test on the 8th.